All right, welcome. This is our final video, our final topic in our Liquids and Solutions unit. You're going to need your reference table open to, your notes open to page 27, and that's actually all you're going to need for this. We're going to be talking about something called colligative properties. What is it, and what are its effects? Colligative property is a property of a solution that only depends on the number of the solute particles and not the type, i.e. it's something about the solution that is affected by the fact that there is a solute present. And there are a number of different colligative properties, but there are two specific ones that we will be concerned with, something called freezing point depression and something called boiling point elevation. So really from this point forward, I'm just going to be referring to those two things. They are properties of solutions that are impacted by the number of solute particles and not the type. So first up, freezing point depression. What is freezing point depression? Freezing point depression is the idea that if you add any solute at all to a liquid, it will lower, i.e. depress, because depress means to lower the liquid's freezing point. You put a solute in a liquid, the freezing point now becomes lower than it had been before, meaning that your liquid with the solute will now be a liquid at lower temperatures than it was capable of being a liquid at before. This is why we put salt on the roads on the ice in winter, because by putting salt on, you're adding a solute and it's actually lowering the freezing point of the water. So instead of water freezing at 32 degrees Fahrenheit, now water might freeze at, let's say, 25 degrees Fahrenheit, which if it's 28 degrees outside is going to be very useful, because what the salt is doing is melting the ice. It's making the water freeze at a lower temperature. Boiling point elevation. What is boiling point elevation? If you add any solute to a liquid, any at all, it could be anything, it will raise, i.e. elevate, that's why we call it boiling point elevation, it will raise the liquid's boiling point. So any solute at all that you put into water, water's boiling point is 100 degrees Fahrenheit. 100 degrees Celsius. You put any solute at all in that. Now you're going to push the boiling point to be a higher temperature. So it will stay at a liquid at higher than normal temperatures. You put a solute into water, water won't boil at 100 degrees anymore. Now it'll boil at a higher temperature. So it'll be like 102 degrees and it'll still be a liquid and it won't be boiling if it's got a solute there. That's colligative properties. To put this graphically, what does this mean? So we have this little graph right here. So we've got temperature on the y-axis. So let's say we've got just liquid water. So maybe this is 0 degrees Celsius and this is 100 degrees Celsius. So that's the freezing point and the boiling point of liquid. Just water on its own without any solute added. But then we add a solute. What that's going to do is drop the freezing point, make the freezing point be lower, but it's also going to raise, at the same time, it's going to raise the boiling point. So this is our boiling point, this is our freezing point, this is our new boiling point of the solution, right? Not the liquid. And this is our new freezing point of the solution, not the liquid. And what we can see is that the liquid on its own, this is the area when it's in the liquid phase, because down here it's going to be a solid and up here it's going to be a gas once it passes its boiling point and then drops below its freezing point. But then if you make it into a solution, now we have a much larger area where it is a liquid. You've increased this area up here. It's going to be a liquid at temperatures it isn't normally a liquid at. And likewise down here, where it's normally a solid, you've increased that area. You've raised the boiling point, higher boiling point, and you've lowered the freezing point, i.e. solutes make solutions last as a liquid longer. There are more spaces over here where it's a liquid than it was before. You've increased the temperature region where your thing is a liquid. A solute raises the boiling point, it lowers the freezing point, it makes your solution behave as a liquid at over a longer region of the temperature scale. So big point. Absolute key points about freezing point depression and boiling point elevation. The more concentrated your solute, the lower your freezing point is going to get, i.e. the more freezing point depression, and the higher the boiling point is going to get, i.e. the more more boiling point elevation. The more concentrated, the more effect we see. The more solute particles you have, the lower the freezing point will get, the higher the boiling point will get. When the whether people say that it's so cold outside that salt doesn't work on the roads, they are lying. They are 100% lying. That is so not true. Salt will continually lower the freezing point. What they mean is that it is so cold outside that in order to melt the ice, we would have to put so much salt on the road that it no longer becomes economically feasible to do so, when we might as well just wait a few days for it to warm up, which is cheap because it's free. So when they say that that salt doesn't work, they lie. What they mean is we'd have to put so much damn salt on the road that we're not going to do it because it costs too much money, because of this point right here. The more stuff you put into, the more solute you put into your solvent, the lower the freezing point will get and the higher the boiling point will get. The second point here, the more particles that a solute dissolves or dissociates into, the lower the freezing point, the higher the boiling point. What do I mean by that? Well, sugar, this is covalent, so it does not dissociate, right? It doesn't split up into ions, so this is just kind of like one particle. But NaCl, now this is ionic. So when you put this NaCl in water, we get Na plus and Cl minus, i.e. we get two particles. And this is why we put salt on the road rather than sugar. A, salt is cheap because we can get it from ocean water fairly economically, but also when we put NaCl on the road, it splits into two particles, and that essentially gives us a doubling effect for this freezing point depression and boiling point elevation. So salt is really, really good at doing this. Calcium chloride, on the other hand, this is also ionic, but calcium chloride will dissociate into calcium ion plus a chloride ion plus a second chloride ion. That's what that 2 right there is saying. So here we actually have 3 particles. Again, only ionic compounds can do this. Sugar can't do this because it's covalent. So calcium chloride would be even better than NaCl on the roads because we get more particles. And the more particles we have, the lower the freezing point, the higher the boiling point. The more particles our ionic compound can dissociate into, the better this process will be. We don't put calcium chloride on the road because it's expensive. But if you have that like super melt stuff at your house, the stuff that's, works at temperatures that rock salt doesn't work on, I guarantee you all it is an ionic compound that will dissociate into more than 2 ions. Like guaranteed. You look at that formula, that's what it's going to be. So how does this work? Why does a solute why does a solute lower the freezing point of a solution? Why does a solute raise the boiling point of a solution? Well, what's happening, it's actually all about the IMFs. In order to freeze, the solvent has to form IMFs with itself. It has to come together and solidify. So it's forming these interactions. The presence of a solute particle will get in the way. The solute particle prevents the liquid from forming the necessary intermolecular forces of attraction to freeze. Solute disrupts IMFs. It keeps the water from basically sticking to itself. The water would rather stick to the solute than to itself. And if it can't stick to itself, it's not going to freeze. Boiling point elevation. Why does boiling point elevation work? Why does the presence of a solute prevent the liquid from boiling? Because that's essentially what it's doing. It's keeping the liquid in the liquid state and preventing it from going off and being a gas. Exact same idea. The presence of the solute prevents the solvent from leaving. The water will form IMFs with the solute. That will require more energy to separate from. So it becomes harder to get the water to break that attraction and leave. So we have here, this is the seawater, we have lots of IMFs, in this solution, and the water does not want to leave that. The water wants to stay sort of stuck to the solute particle. There's going to have a stronger IMF with that. Versus pure water, there's no solute there that that water is going to have a really strong attraction to, so there's no reason to keep water basically in the liquid form. It's all about the solute. The water would preferentially form an IMF with the solute than itself. So by having that solute there, it sort of keeps the water in the liquid phase at a greater temperatures, at higher temperature and a lower temperature. Keeps it as a liquid longer. So some Regents questions about colligative properties. Which of the following solutions would have the lowest freezing point? So we have these options: 0.1 moles of an ionic compound in 100 mils of water, 0.1 moles of covalent in 100 mils of water, 1 mole of ionic in 100 mils, 1 mole of covalent in 100 mils. First thing you want to do is eliminate the choices that have a covalent compound. Because remember, an ionic compound dissociates into multiple particles. And that's good. The more ions, the more particles your substance dissociates into, the lower the freezing points, the higher the boiling point. Lowest freezing point, that's the same thing as saying most concentrated. Too, right? The more stuff you have, the lower the freezing point, the higher the boiling point. So we're eliminating choices B and D because they are covalent. Right, they're covalent, so we don't want to pick them. We want to leave our choices up with ionic things. And then it comes down to A versus C, and the difference there is 0.1 moles versus 1 mole. It's saying how concentrated is our solute? How much solute do we have? We want the most concentrated one, so we're not going to choose A, but we are going to absolutely choose C. We're choosing C because it's ionic, and we're choosing C because it has the most solute dissolved. 1 mole dissolved in 100 milliliters versus 0.1 mole dissolved in 100 milliliters. Next up, compared to a 0.1 molar aqueous solution of sodium chloride, a 0.8 molar aqueous solution of sodium chloride has what? First up, we're comparing a 0.1 molar solution to a 0.8 molar solution. Comparing these two on their own, this is a lower concentration, this is a higher concentration. And now, with that in mind, we can look at the choices. We notice the choices are all about boiling point versus freezing point. The more concentrated, the higher your concentration, the greater the effect of boiling point elevation is going to be. The higher your concentration, the lower the freezing point, the higher the boiling point. Remember, it makes the liquid be a liquid under greater circumstances, lower temperatures and higher temperatures. It pushes the freezing point down, raises the boiling point up. So we're looking for a choice that matches with this. Choice A, higher boiling point. Well, that's good. We want that. And a higher freezing point. No, we don't want a higher freezing point. We want a lower freezing point. Next one, higher boiling point and a lower freezing point. That's exactly what we want because that is going along with this. Just looking at C, C is wrong because it will not have a lower boiling point. It will have a higher boiling point, and it will not have a higher freezing point. It will have a lower freezing point. And then D is wrong, again, because of that lower boiling point. The lower freezing point, yes, that's true, but it's not paired with the correct thing. So that's colligative properties. We're going to be doing a web lab with colligative properties and a demo with colligative properties.